Hello everyone. Let me walk you through this week's highlight on charges, the force between charges, and electric fields. So here I have some fundamental particles. This is our atom here. We have a bunch of protons and neutrons in the nucleus, and we have the electrons that are orbiting around it. And so here I've had a table where I list the charge of these objects and their masses. So I want to highlight here the fundamental charge is E, which is 1.6 times 10 to the negative 19th coulombs. So a proton has exactly positive E, an electron has exactly negative E, where a neutron has a zero net charge, okay? Now I've listed the masses here. If you notice, the mass of a proton is listed as the same as the mass of a neutron. A neutron actually has slightly more mass than a proton does, but to three significant figures they're the same, and so we're just going to use the same value here in this class when you need it. Electron has much less mass than these two have, as you see here, 10 to the negative 31th instead of negative 27th. Now, here I have two positive charges that are held by strings to a ceiling. And in an experiment, we see that two positive charges are actually going to repel each other. They're going to apply a force, pushing them away from each other. If I have a positive and negative charge, these apply an attractive force. So there's a force pulling them together. And even if they're both negative, they're also going to apply a repelling force. So like charges repel, whether they're both positive or both negative, and opposite charges attract each other. So one positive, one negative, it applies an attractive force. Now, I'm going to draw some charges here in the next few slides, and I want to highlight something. All of matter is made up with a huge amount of positive and negative charges. But typically, all those charges are neutral, meaning there's just as many positives as negatives. When that's the case for this metal sphere, I'm not going to draw any charges on it. Even though it's made up of a bunch of positive and negative, it doesn't have any excess charges. So here this metal sphere has some excess positive charges, meaning that some of the electrons have left. So it's only going to be the electrons that are going to be moving. The nucleus, where all the positive charges are, is kind of held in place by the crystalline structure of the object. So here I have some positive ions. Ions just means it has excess positive or negative charge. So because it has some excess positive charge, I'm going to draw the positive symbol here. Now, it doesn't mean it doesn't have negative charges. In fact, there's a huge amount of negative charges here, but there's no excess negative charge. For every negative charge, there's a positive charge, and these are the positive charges that don't have negative charges with them as well. On this side, this has some excess negative charges. So I've drawn some excess negative symbols here. This means that some electrons have been added, so there are some atoms here with more negative charges than positive charges. Again, it doesn't mean that there's not positive charges here. In fact, there's a bunch. It's just that there's not any excess positive charges. So we're only going to draw the excess charges. So here I have a metal sphere that has positive ions and a neutral metal sphere. Now what's going to happen when I apply a metal nail here on top of these two metal spheres? Well, there's electrons here in this metal that can kind of freely move around, and there's an attractive force towards these positive ions here. So when I put the metal here, those electrons are going to be are going to receive an attractive force to these positive ions. They're going to travel up and through the nail and into this other metal sphere. Now, when these electrons leave, they're going to leave some positive ions behind. So they left an atom that now has excess positive charge compared to its negative charge. And on this side, when those electrons enter this metal sphere, they're going to enter some atoms that had some excess positive charge that now are going to become neutral. So in the end, we're going to be left with some positive ions on this side because we lost some electrons, and less positive ions on this side because some of those electrons made some of those atoms neutral. Now, what's going to happen if I put wood on top of these two metal spheres? Well, nothing, because wood is not a conductor, meaning that electrons cannot travel freely through the wood that it can with metal. And this is what's called an insulator. So we're going to have two types of material that we're going to talk about in this class. Conductors, which are metals, where materials that can easily transfer charge through them, and insulators like wood or plastic, materials that will not easily transfer charge through them. Now, there is a class in between called semiconductors that are not really good insulators and not really good conductors. We're not really going to talk about those in this class today. We're just going to deal with conductors and insulators, okay? Now, here I have this negatively charged rod, and I'm going to bring it close to this metal sphere, this neutral metal sphere. So this is full of positive and negative charges, but there's no excess charge, so I'm not drawing it. So when I bring this negative rod close, there are some electrons here that are going to be repelled. So negative charges repel negative charges. So when I bring it close, you can watch. Okay, they move to the other side. So they were right on top of their atoms before, but when I brought this close, the negative charges receive a repelling force from this negative rod, pushing them to the other side. Now, when they go to the other side, they leave behind positive ions, which is what I'm drawing here. So when a charged object is brought close to a metal sphere, a conducting sphere, or a conducting object, the object becomes polarized. Polarized just means that the charges are moved to one side, leaving behind the opposite charge on the other side. Now, what is the actual force? Like how many newtons of force is happening here between these charges? And that is determined by Coulomb's law. F equals K, Q1, Q2 over R squared. Now, F, this is just the magnitude of the force between the charges. This is the newtons. K, this is Coulomb's constant. It's a value 9 times 10 to the ninth. Again, think about this as a unit conversion between these two things. Q1, this is the charge of particle 1. Q2, this is the charge of particle 2. And R, this is just the distance between those particles. Now, this just gives us the magnitude of the charge between them. See this symbol here? This is the magnitude symbol. So if this term here ends up being negative, the magnitude makes it positive. So Coulomb's law just tells you how many newtons. It doesn't tell you the direction. To determine the direction, we have to look at the orientation of our particles. So here I have two negative charged particles. Because they're both negative, they're going to apply a repelling force. So the force is exactly opposite of the location of the other charge. Here on this side, I have a negative charge and a positive charge. Because these are opposite charges, they receive an attractive force. So the force is directly towards the other charge. So I use the orientation of my particles to determine the direction of the force, and I use Coulomb's law to determine the magnitude or the amount of the force. All right, let's do a problem. Here I have two charges, charge Q1 and Q2. This has mass M1 and mass M2, and I give you the mass of both of these and the charge of both of these, as well as the distance between the two. And I want to know what is the magnitude of the force between these two. So I can use Coulomb's law, K, Q1, Q2 over R squared. So I can just plug in our values here. K is 9 times 10 to the ninth. Q1 is this negative 5.6 number. Q2 is this 1.4 number. And R, the distance between the two, is 0.4. So I can plug all of these into our calculator, remember, this is the magnitude, and I arrive at a force of 0.441 newtons. Now, what is the direction of this force? Well, one is negative, one's positive. I'm asking for the direction of the force on Q2. So, meaning that Q2 is going to receive an attractive force from Q1, so the force is going to be to the left. My next question is, what is the acceleration of particle Q1, the particle on the left? We've got to think all the way back to Newton's laws. So if the force of attraction is 0.441 newtons, meaning that this particle receives a force to the left by this particle, then this particle, Q1, receives a force to the right due to the other particle. So from Newton's third law, F equals 0.441 newtons to the right. So this Q1 receives 0.441 newtons to the right due to particle Q2. Now, to get the acceleration, I can use Newton's second law, F net equals ma, and I can solve for a. A equals F net over m, and so I can plug in the net force, which is 0.441, the mass of particle m1, which I tell you here is 0.3 kilograms. I plug those in, and I get an acceleration of 1.47 meters per second squared to the right. Charged particles also generate an electric field around it, and other particles are going to, that are in that field, experience a force. And the force they experience is due to their charge and the electric field. So F equals QE. This Q is the charge receiving the force, and E, this is the electric field generated by other charges. So the units of E are going to be newtons per coulomb. So let's say a proton is in an electric field that has a strength of 4.5 newtons per coulomb. What is the magnitude of the force on the proton? Well, F equals QE. Q for a proton is the fundamental charge, 1.6 times 10 to the negative 19th. And the electric field I told you is 4.5 newtons. I multiply those together. 7.2 times 10 to the negative 19th newtons is the force that this proton receives. Well, I just told you that this is the electric field generated by other charges, but how can I calculate what that electric field is? So that we can determine that by going back to Coulomb's law. We have F equals QE and F equals K, Q1, Q2 over R squared. I'm going to rearrange Coulomb's law by bringing Q1 out in front. So I can multiply or divide things in any order I like. It doesn't change the result. So I'm going to bring Q1 out front. I'm going to add some parentheses here around K, Q2 over R squared, which is what is left. And if you notice, there's some similarities here between Coulomb's law and our F equals QE equation. Well, these Q's are in the same spot, and you notice how the electric field is in the spot of KQ2 over R squared. And so this is going to be our equation for an electric field. E equals KQ over R squared. This Q, this is the charge that's generating the field, and this R, this is the distance from the charge generating the field to the point we're interested in. So if I have a charge and I want to know the electric field at a point, I can plug those numbers in. Now, for each point, as you look in different points, there's gonna be a different electric field there because you got to plug in a different value for R. So let's say, what is the electric field a distance of 8.2 times 10 to the negative fifth meters away from a proton? Well, I can just use this equation, E equals KQ over R squared, where K is 9 times 10 to the ninth, Q is the fundamental charge for a proton, and R is the distance that we're interested in. And so I plug all this into our equation, and I arrive at an electric field of 0.214 newtons per coulomb. Here is the summary slide for this week's highlights. We have our fundamental charges here, as well as their mass. I give you the value for the fundamental charge. Coulomb's law, the force between two charges. F equals QE, the force on a charged particle due to an electric field. And then E equals KQ over R squared. This is the electric field that's being generated by a specific charge. All right, I hope this helps.